All right, welcome. Today, we're going to tackle a really important topic for your NEET prep, pressure in fluids. Seriously, understanding this is key to nailing some important questions. So let's just jump right in.
So, let's start with a question you've probably never really stopped to think about, but you've definitely experienced. Why is it so much easier to slice an apple with a sharp knife compared to a dull one? I mean, with a blunt knife, you're pretty much just crushing the thing, right? You're pushing with the same force, but you get totally different results. What's going on there?
Well, the one-word answer to that is pressure. That's the physics concept behind it. It's a huge deal in mechanics, but it's especially critical when we start talking about fluids. So let's really get into what pressure actually means. Okay, first up, pressure, the basics. We got to start here. What exactly is this thing we call pressure?
So here's the textbook definition you absolutely need to have locked in for your exams. Pressure is the normal force, and you can also think of that as thrust, that acts on a certain area. The big idea here isn't just about how hard you push, it's about how spread out that push is.
And this all boils down to one simple, powerful formula. Pressure, or P, is just force, F, divided by area, A. P equals F over A. Seriously, this little equation, it's the bedrock for everything else we're going to cover. So get comfortable with it.
Okay, let's break that formula down a little. It tells us two really important things. First, pressure is directly proportional to force. That makes sense, right? You push harder, you get more pressure. But, and this is the part you really got to get, it's inversely proportional to area. Meaning, if you take the same force and squeeze it into a smaller area, the pressure goes way up. Oh, and the SI unit we use is the Pascal, which is just 1 Newton of force spread over 1 square meter. Now here is a huge fact for NEET, so listen up. This is a classic trap. We know force is a vector, right? It has a direction. But pressure is a scalar quantity. It has a size, a magnitude, but no direction. At any single point inside a fluid, the pressure pushes out equally in all directions at once. Remember that. All right, enough with the theory for a second. Let's look at pressure in everyday life. This is where all those concepts and formulas suddenly click and start to make sense. So, let's go back to our apple cutting mystery. The sharp knife has a teeny tiny area of contact at its edge, so all the force you're applying gets concentrated right there, creating this massive pressure that slices right through. The blunt knife, it has a much larger area, so that same force gets spread out, the pressure is way lower, and, well, you just end up with a bruised apple. And it's the exact same idea when you try to walk on sand. Think about it. With flat shoes, you have a big surface area. Your weight gets distributed over that whole area, so the pressure on the sand is low, and you walk on top of it. But with sharp heels, all your weight is focused on that tiny point. That creates enormous pressure, and you just sink right in. It's all about that force over area relationship. Okay, so we've got a handle on pressure on solid surfaces. But this section is about fluids. So what happens when we're talking about the pressure inside a liquid, like water? How does that work? Let's dive in. All right, have a look at these 4 containers. You can see they've all got different shapes, right? And they're filled with water to different levels. Now here's the question for you. In which one of these vessels is the pressure at the very bottom going to be the highest? Take a second and think about it. Okay, got your answer? The pressure is actually greatest in vessel D. Yeah, D. And it's lowest in C. Now, I know this can feel a little weird at first. You might think the shape or how much water is in there matters, but it doesn't. The only thing that counts for pressure at the bottom is the vertical height of the fluid column. So why is depth the only thing that matters? Well, in a fluid that's just sitting still, the pressure is the same everywhere along any horizontal line. But as you go deeper, the pressure increases. And that brings us to our second super important formula. The pressure difference between 2 points is equal to H times rho times G. Here, H is just the vertical depth between the points. Rho, that's the Greek letter, is the density of the fluid. And G is, of course, acceleration due to gravity. So simple. Shape of the container doesn't matter. It's all about that height. Okay, section 3, your NEET power-up. This is where we get really strategic. I'm going to highlight the absolute must-knows for your exam and the common mistakes you need to avoid. Okay, this slide is gold for your exam, so really focus here. First point, we've said it before, but I'll say it again, pressure is a scalar. Don't forget it. Next trap, don't mix up pressure with force. They are not the same thing.
Now for the big one. That formula, H rho G, that calculates the extra pressure you get from the depth of the fluid. But if a question asks for the total or absolute pressure, you have to remember to add the atmospheric pressure that's pushing down on the top of the fluid. So many students forget this, and it's an easy way to lose marks. Don't let that be you.
All right, time to put the theory to the test with a quick problem. This is exactly the kind of thing you might see on the exam. So imagine you have two thigh bones, femurs, each with a cross-sectional area of 10 square centimeters. Together, they're supporting a body with a mass of 40 kilograms. The question is, what's the average pressure on those bones? Okay, let's walk through this. Step 1, we need the total area. Since there are two bones, we have 2 times 10, which is 20 square centimeters. And this is critical. We have to convert that to square meters. So that's 20 times 10 to the power of minus 4. Step 2, we need the force. That's just the weight of the body, so mass times g. We'll use 10 for g to keep it simple. So 40 kilograms times 10 gives us 400 newtons. And finally, step 3, we just plug it all into our formula. Pressure equals that 400 Newton force divided by our area. And when you run those numbers, you get our final answer, 2.0 times 10 to the power of 5 pascals. That's a pretty significant amount of pressure those bones are handling. Okay, let's do a super fast 10-second revision. What are the two big takeaways? Formula 1, pressure is force divided by area, P equals F over A. Formula 2, the extra pressure from a fluid's depth is H times rho times G. If you can remember just those two things, you're in a great spot. All right, before we wrap up, I want to leave you with a little something to chew on. We've hammered home the point that pressure is a scalar, right? It has no direction. So why is it that the force that a fluid exerts on a surface is always perpendicular to that surface? Think about it. What would happen if a part of that force was acting sideways, parallel to the surface, in something that, flows? It's a great question to test your understanding. Mull that over, and we'll catch you on the next one.